the next section is called Interpreting Climate Change Projections, but I'll cover some aspects of this here, but there'll be a lot more about that when we get onto some case studies and some practical examples with Leanne after this. But this is, again, kind of just some background and in theory about this kind of topic. And this builds upon, of course, the things I was just talking about before about understanding the different sources of what causes the possible future climate change, ongoing variability, emission scenario, emissions pathway we follow, and then also what the response of the climate system is to those emissions, and how that's different in different places and different scales and for different aspects of the climate. So I'll just get my computer to wake up. Go to the next slide. So, of course, because we don't have a single view about what the world will do and what the resulting emissions is, it's always best to kind of consider a range of possibilities to assess a range of plausible emission pathways and the type of world that gets you there. So, for example, a world in which we go to net zero carbon emissions has lower climate change because there's lower effect on the climate, this RCP 2.6, but it also has profound effects on the type of world we live in because there's no longer, widespread use of fossil fuels. There's also, very different practices in other emissions-intensive industries like concrete and steel and so on, to get those emissions down to that level, compared to, say, a very high emission scenario or emissions pathway where there's very high and extreme levels of physical climate change challenges to adapt to the changing climate, but there's been lower challenges from mitigation because we just simply haven't done it. So thinking about a range of possibilities of the physical climate change, but also the world that got you there is always smart, because you don't want to count on one particular one coming true and ignore all the others. But there's often a lot of discussion, debate, speculation about, but surely that one is implausible, or that one, that's crazy, we can't get to that one, or this one's probably the most likely, isn't it? And I'm just going to show one little bit of analysis here. But before I do, I want to make it really clear that we can't say how likely any of these are really, because they depend on not only what's already happened and what's happening now, but what will play out in years and decades to come. It's likely that none of these will play out exactly as laid out. There'll be kind of fits and starts and kind of changing, turning corners, etc. But it's still a good idea to kind of take into account a full plausible range of change from low to high. This is an analysis of the last year's International Energy Agency report, which perhaps people on the line are familiar with, which was a really interesting piece of work. This was an analysis of that report done by Zeke Housefather at Carbon Brief. So take this as what it is. It's an analysis by a group of the particular IEA projections. And this is what they kind of came up with in terms of likelihood given current policy. So this is if the current policies play out, or if the pledges are played out, this is what seems likely. But if there's a change in policy, or the pledges are not met or exceeded, then obviously this changes. But given the current policy, it seems like it's now highly unlikely we'll actually get onto that worst case scenario. Also, this really shouldn't be called business as usual, because there's no as usual anymore in the world today. And this very high scenario, the highest plausible scenario in a way, with no policy and emissions go back to accelerating, is not what I think anyone would call a business as usual. We're just locked in on that path. So that terminology has kind of changed a little bit, I think rightly so. It also seems less likely that we will be on a high emission scenario, something like RCP 7 or SSP 3.7 in the new terminology, which would involve a reversal of some current policies. It seems more likely we'll be on something like a level of 6 or 4.5, RCP 4.5, RCP 6 or SSP in the emerging new structure. given the current policies. And this will still lead to something like 2.5 to 3 degrees of global warming by the end of the century, so exceeding the Paris Agreement limit. To get onto the mitigation pathway required to meet the ambitious Paris goal of 1.5 degrees requires an emissions pathway lower than the previously mentioned RCP 2.6, something like SSP 1.9, so even lower than 2.6, which also looks very unlikely given the current policies. But who knows what's going to happen over the next 10, 20, 30 years? Maybe that will become more plausible. We'll just have to see. So again, take this for what it is. It's an analysis of what appears to be likely given current policy. We can't say for sure which is actually more likely in the long run. And we should also still kind of, from a risk management point of view, still play out what is the consequence of following this unlikely but possible very high scenario. For a given scenario, that previous plot kind of showed the average or the kind of consensus view of consensus. What's the word? Yeah, the midpoint of what the global warming is likely to be. But there's a range of possibilities. And when you go down to regional scales, there's a broader range of possibilities. So, for example, in a very high emission scenario, RCP 8.5 for Australia, the range gets quite wide towards the end of the century because we just don't know, exactly how high the climate sensitivity is. Is it more like 4 degrees or is it more like 6 degrees? These are very different kind of outcomes for Australia, and you wouldn't want to stake everything on one end being true and the rest and ignore the other ones. Or worse, just look at one and not even be aware that there's other possibilities. So therefore, for a given emissions pathway, it's always smart to either examine all the possibilities and all the kind of modelling that's available for that scenario, or at least select a representative subset that kind of accounts for that range of possibilities. So a high, medium and low within that range, for example. And this is always the principle that we suggest to do, because otherwise you might present something that's kind of overconfident in a particular outcome, and that can lead to maladaptive decisions. So for example, if you say it's definitely going to be 6 degrees warmer by the end of the century, that's taking a very extreme case from a very high emissions scenario. And if you put all your eggs in your basket to adapt to that, then you're going to be doing some excess adaptation, very likely. Whereas if you say it's definitely going to be the lowest emission scenario, the world's going to get onto that track, and it's going to be the lowest emissions pathway for that. It's the lowest outcome for that emissions pathway. Then you're also similarly being overconfident on a very good outcome, and you'll do some adaptation decisions that are inappropriate and not accounting for the range of possible risk. And I know you guys are probably more versed in the kind of language and concepts of risk management than we are. So I'm sure all of this kind of talk is very familiar to you. So for an example, here's some bar charts of change by the end of the century for Eastern Australia for temperature on the left and rainfall on the right by season, with the different emissions scenarios in green, blue and red. And you can see the little symbols in there are a set of 8 models chosen to give you that representativeness of the full set of over 40. Because people don't want to number crunch 40 if they don't have to, if they can do fewer. And this 8, or even a smaller subset of these 8 can be really useful to still give you that kind of idea of the range of possibilities. And you can see some of these symbols are actually below some of the bars for some of them, and that's because these bars are just the 10 to 90% range. So this also samples some of these outliers, the very hot or the very dry ones, which can be also your edge cases, if you know what I mean, or the kind of worst case cases. So this principle, I hope, using this simple example of temperature for all of Australia, or this detailed example of temperature and rainfall for Eastern Australia specifically, gives the idea of, if you just use one of those, you know, it's a scenario, it's a plausible scenario, but it's not at all accounting for the range of risks. Another aspect of using climate change projections is to understand the confidence. So this is slightly different than those other three sources of uncertainty I mentioned: internal variability, the emissions scenario, the range of change, possible change for each scenario. This is our confidence in the underlying science or the underlying processes overall. So we look at model results, we look at the evaluation of models, how good models are at doing this. We look at high resolution or downscale modeling to see how well that agrees. We also look at past trends, observed trends in those things to see what we can glean from that. We also have a critical look at what we understand about the climate process driving that change. And this informs a confidence assessment. This can be really useful in that it kind of tells you with what confidence to use these numbers at all. So, for example, on average temperature of the world increasing, we kind of give that a rating of very high confidence, or in likelihood terms, virtually certain, which means you can use that piece of information with real confidence. Whereas some other things, say, for example, the incidence of tropical cyclones moving further south down the East Australian coast, we don't have very high confidence. It's not virtually certain, but there is some evidence for it, and so therefore we might give that a rating of, say, medium or confidence. That means it's a plausible possibility that should be taken into account, but you can't, you know, stake all of your chips on that thing coming true, if you know what I mean. Model evaluation is part of this, of course. This is where we compare observations to the model and see where and when it falls short, or it gives a kind of a poor representation. At the broad scale, models look fantastic. This is average temperature in the last 20 years of the 20th century, and you can barely see any difference between models and the observations. But when it comes to more subtle things, like, you know, for example, those extreme events, those storms that bring the highest, you know, wind speeds, you know, that's a much more challenging thing to simulate, and the evaluation won't look quite as good. That will affect your confidence rating. Yeah, kind of. I should have mentioned this before, but like, to come up with that rating of very high, medium, low confidence, we look at not only just the different types of evidence, so the type, amount, quality and consistency of the evidence, but the agreement between different lines of evidence. So, for example, if you have a group of climate models, half of them say one thing, half of them say the other thing, we're not clear about the dominant physical process that would drive change one way or the other, then that's poor agreement. There's poor levels of evidence and poor agreement, so that's low confidence. Whereas if we've got high agreement between, you know, past trends, models, and we've got a good physical understanding, all of those points the same way, we've got good lines of evidence and good agreement between evidence, that's very high confidence. So these confidence ratings are really important. And here's an example, a really current example. So in Texas last week, there was this cold outbreak, led to a lot of problems on the electricity grid. I'm sure you guys were looking at that with interest. There were some articles saying that, oh, cold outbreaks are becoming more likely because of climate change. Other people are saying, well, hang on, no, they're not. That's not true. And this was an example where there was some evidence that as Arctic sea ice melts, the jet stream becomes more wobbly, and we can actually get big cold outbreaks hitting, you know, further south than before, could lead to this. That this is a kind of an area where there's low confidence, there's not a lot of evidence, and there's not a lot of agreement in between the evidence, but it's a possibility. And so this is where it shouldn't be reported as fact, and it shouldn't be reported as it's definitely not true. It's one of those cases where there's some evidence, but, you know, we need to kind of look at the balance of evidence and look at the balance of risk and take it with that, in that spirit. And that's about something that's happening now. It's the same for when we look into the future. So what's going to happen? Like, some things are very clear and very confident that they will happen. Some things, they're possible, but, like, you know, we have to give that low confidence. And therefore, if it does happen or if it doesn't happen, you can't kind of say, hey, you said it would happen, because it's something that, you know, it's possible, there's evidence for it, but it's not clear, and that just needs to be inform how you make decisions in response to that evidence. Another aspect of using climate projections is global climate models are quite coarse. They give global scale and continental scale and regional scale kind of information. But to turn this into something that you can use at your house or at your site or on your network, we need to do things to make them ready to use in applications and make them locally relevant. So accounting for the influences and the effects at scales smaller than 100 kilometres. They also need to be application ready, so unbiased or calibrated to the observed data sets we use to look at the current climate, because if they've got a difference, then that's makes them not possible to use. There's many ways to make locally relevant application ready data sets to use to play out a particular climate scenario on the ground. And this involves many choices. So you can do further statistical or dynamical modelling at the regional scale. You can employ various types of post-processing. You can get observations, combine that with the change information from climate models and do something either simple or complex to that to produce a data set, or you can employ bias correction. So downscaling bias correction of actual model output to produce a nice looking data set. And there's no one right answer. Each of these have got their pros and cons, and each of them are applicable to different questions to different degrees. Just to give you an idea of the very simplest method, which is still really useful for many things, if you're interested in the change in the average, so what the average climate is over a 30 or 20-year period in the past compared to the future, and where things like, say, the boundary between where something's cooler than 25 degrees or cooler or warmer, or where the average snow line will be on a mountain, etc. What you can do is take the observed climate using good quality, high resolution observations and data sets that we have. You can simply apply a change factor or a delta scaling to that to get a future picture of the climate with that change applied to it. And you can see, a change in the boundary of these different climate zones, etc. This is a really simple but really useful technique, and you can go up from there. You can go up to incredibly sophisticated dynamical regional modelling with sophisticated multivariate bias correction to produce very sophisticated data sets. But I think it's really important to keep a couple of things in perspective and keep your kind of 30,000 foot overview of the situation when you use any data set. And that is, these are projections given a particular assumed set of scenario of change, that the likelihood of that scenario or not, or the fact that it's a scenario needs to be kept in mind. The fact that it's also one sample of the possibilities for that emissions pathway or scenario also needs to be really clearly kept in mind, because and then also what are the other aspects of the data set you're using? What can it do? What can't it do? Because you can make some really nice looking graphics out of future projections, and that shouldn't kind of mean that you're kind of think that therefore it's more accurate if it looks nice and it looks at a high resolution. You've always got to keep a critical eye on that big picture and the sequence of events that got you there. So, but just after that kind of word of warning, before we delve in, I'll just give you a little bit of detail about some of these more sophisticated methods that do have value. One is high resolution modelling of the region of interest using those global climate models as input. So here's an example of going from a global climate model through different scales down to very fine scale using the CSIRO regional model to CCAM. And you can see that coastline, the topography, a lot of aspects become a lot more realistic looking. And this can potentially give you really important new and good information about climate change at the regional scale, what's happening on the mountains compared to what's happening at low elevation, for example. But we need to then also understand, well, where is it giving you new information? Not just nice looking regional information, but new information about what's likely to change. Because we can make these nice looking data sets using simpler methods. This is a study that we published last year, which I think was directed at this and is hopefully very useful. And this is what we called realized added values. This is where the current climate is simulated with more realism in the regional model compared to the global climate model. And also it gives you a different projection. It modifies that change in a kind of a consistent way. And so therefore there's evidence that it's giving you something really valuable and new. And where is that highest? That's over the areas where you expect, over mountains, small diverse regions like Tasmania, also some areas of northern Australia. And some of these include the Alps region of eastern Victoria and New South Wales shows high added value. And that's because it's simulated better, the flows over mountains, etc. And there's a projection of enhanced decrease on the slopes of the mountains, so even drier on the slopes of the mountains compared to the lowlands. And that's very plausible given the physics of rainfall in the region and its response to a warmer atmosphere. So yeah, as I was saying, dynamical downscaling looks great, gives you great spatial detail, gives you great temporal detail. You can start drilling into sub-daily data sets and hourly data sets, and it makes visualization really easy and nice. So for example, I've got a future heat wave playing out over 4 days here on the right in Southeast Australia in the year 2057, as an example, where you start getting multi-day heat waves getting really walloped there with up over 50 degrees under this kind of plausible future scenario. But it's always important to remember and to consider that are the data sets you're using representative of the emission pathways you want to use? Is it representative of the range of possibilities for each pathway? And is it changing the change signal? And is it doing that for the better or for the worse? And also remember that post-processing is still needed once you've got that output. And this is kind of where we start hitting some really practical issues about using data and information for the ESCI case studies, because there was recognised to be real value in this regional modelling and dynamical downscaling. And we have done some work to kind of address some of these aspects about representativeness of those data sets and how to interpret and use them, and to kind of recommend a set that meets those kind of requirements to use, but to be used mindfully. So there's just a couple more links about what I drew on. I drew on some other things, but there's a couple of more. So Beck, should we stop for Q&A again?
Yep, that sounds good. There is just Jill has asked in the chat, can we talk a little bit more about how downscaling works? Like take the data point for a 100 by 100 kilometre grid from a GCM and then integrate that into a single point into smaller grids.
Yeah, I kind of glossed over it, didn't I? I just kind of showed the grid size rather than actually telling you about it. So yeah, there's two distinct forms of downscaling. So there's the simple delta scaling, which is what we call just scaling, using observations and scaling them up or scaling them down, or you can do it more complex way than that. Actual regional modelling, or modelling the regional climate using the global climate models as input, there's two distinct categories. There's statistical and then there's dynamical. So statistical means taking some of those inputs from the broad global climate model and making a statistical model of your local climate as you know how it's driven by the larger scale. So for example, you might make a statistical model based on the weather system, the pressure pattern, and the kind of temperature gradient or something over your region, which has a good relationship to your local conditions. You can then apply that statistical model to that broad scale climate and produce output. That can be really useful. It's got its own pitfalls, its own strengths and weaknesses, etc. But it can be really useful. The specific one we're talking about here is actually called dynamical downscaling or regional modelling, which means running a similar model than the global climate model. This is one that's got all those equations in it of motion and actually runs a live simulation of the whole system and including the atmosphere, live weather systems, etc. And what it does, rather than start from scratch and just have all of the oceans, everything all in it, and then just run at high resolution, because that takes exabyte computing, it takes the input of the broad scale from the global model and then inputs that as input conditions to a regional model. So it takes the temperature pattern over the surface, it takes other conditions, and then runs the area of interest, or it can be quite a big area, at very high resolution. So it's kind of tied to the global climate model, but it's actually simulating it and playing it out at the local scale using a climate model itself. And that way you can actually get the mountains and kind of the kind of effects of mountains, its coastlines, etc., actually accounted for, while maintaining that broader scale change from the global model itself. But yeah, modelling is always an imperfect art. So it's even though it can go, it looks like it should potentially give you really good new information, that needs to be kind of assessed and evaluated.
Great. And just a follow-up comment that maybe there's a good description in a report, and then we could send that on to people who've attended today. Did anyone else have some kind of question that they wanted to ask?
Hi, it's Tom Livingstone here from AMO. I just had a quick question, Michael. I'm not sure if you can go back to the slide which had like the confidence scale, which was the sort of matrix. Yeah, that's it. So I just want to understand the difference between the y-axis where you've used the word agreement and the x-axis, the final, the fourth component of evidence, which is consistency. So what's the difference between consistency of evidence and agreement? Is there something else in the term agreement that I'm missing?
Yeah, that's a really good question. This kind of matrix is employed in IPCC assessments, and lots of other people have chosen to use it too, because it makes a lot of sense and it's kind of got that broad understanding. So this is something we used in Australia for the national climate projections. We use it often for other projects, and it will be kind of given for ESCI outputs as well. And yeah, so the evidence is the type, amount, quality, and consistency of each type of each line of evidence, and then the y-axis is agreement between different lines of evidence. So, for example, in one of the aspects is physical drivers of change. So, what is the evidence of that line of evidence? Would be what kind of evidence is it? Is it from lab studies? Is it from field measurements, etc.? How many different studies are there? Is there like one study done once in somewhere, or is it like there's hundreds of different studies all done it, or who've all looked at it? How good quality are those different studies, or different kind of measurements, or different lab studies, or whatever it is? And then how consistent is the different studies in terms of that aspect? Then agreement is, well, when you look at all of that line of evidence and you put it alongside, for example, climate model results, does the physical evidence line up with climate model results? And if not, why not? That's where you start looking at agreement between different lines of evidence. Does that make sense?
Yeah, it does. Thank you. That was helpful.
Okay.
Anyone else?
Hey, Michael, it's Leanne. It's an also, so also it's agreement between that the different models also interpret those, so you get it's a model agreement too, like, for example, all the models agreeing that it's going to get warmer. That's high agreement in the models as well. Did you say that, or?
So yeah, I mean, this is kind of that would be kind of agreement between models, which is one line of evidence.
Just the one line, right? Okay.
Yeah. So if the model's a big disagreement between models, then that means that line of evidence is low.
Yeah.
But if you've got, say, high model agreement and it agrees with past trends and physical drivers, that's when you've really got not just consistency and agreement between each line of evidence, you've got agreement between lines of evidence.
I thought it really, if you back up onto that slide of the models on the one more back there, you can see the agreement. All the models are agreeing it's going to get warmer, right? But with rainfall for Eastern Australia, you can see that some models saying it's going to get drier and some models it's going to get wetter. So how would you explain that with regard to confidence, Michael?
Yeah, good question. So you would look at these model results, you'd say that there's not high agreement. So you'd say, for example, winter, spring, there's a medium agreement or some tendency towards getting drier, especially under high emission scenarios, but there's not total agreement. Then you'd also look at past trends and seeing if whether they can be attributed or the cause is clear, and therefore bring in that line of evidence. You'd also then look at, well, what's driving and likely to drive change into the future. So for example, the dominant rain-bearing weather systems, if you know that they are very plausibly going to shift, then that's a really good line of evidence to bring together with the agreement between models to give you overall confidence assessment. So this is all with the idea of a set of models is a really useful tool, but it's not the be-all end-all, and it's not a magic crystal ball. So it's always good to bring together everything we know and to give an overall confidence assessment.
Yeah, and I just noticed a question there from Jill, but I'll just add one thing. So in this case, this is how I would say it, right? So for example, for rainfall for Eastern Australia, it's likely in winter because of the way the models are sort of biasing, or more of the models are showing the drying trend. So we say for winter, spring, likely drier, but we don't say we're sure it's going to be drier. That's where we use the word likely, right?
Yeah, so there's two scales you can use. There's confidence, there's likelihood. So you can say low, medium, high, very high confidence. You can say, you know, virtually certain, very likely, likely, unlikely, for example. Yeah. And both have got, you know, it can be used for sure.
Yeah, and that's how we usually sort of frame things. You'll rarely hear a climate scientist say, well, it's going to be like this. We always have that wiggle room with our statements, and as you should all learn to do when we're discussing future projections, it's always likely to be or projected to, rather than this is going to happen, right?
Yeah, I mean, there's huge debates whether we can even say, you know, climate change is an established fact. That's like, there's,
yeah, I know. So yeah, that's the difference between climate scientists and maybe engineers. I don't know whether engineers are more comfortable with working with that kind of thing. So I don't know. That's a bit provocative in this forum. Anyway, Jill had a question. Yeah, Jill had a question.
Okay.
So I've got a suggestion, I guess, for, you had a great graphic for delta scaling where you had observation plus delta equals change. And I wonder if it's useful to have for downscaling a similar GCM output into, for dynamical downscaling into regional model equals higher resolution or smaller grid scale type data. And I think it would be useful, maybe not now, because, you know, there's a lot to cover today, to explore the climate model into comparison project, to Leanne's point around why we have, let's say, confidence in temperature, more confidence in temperature, because if you like, there's a competition every now and then of global climate models against each other to see how well they agree given the same inputs.
Yeah, so I don't mean like there's a lot to get through, but just one quick point in case it's not clear to people. A lot of our work is based on these sets of global climate models that come out every few years, which are put together by all the different big centres around the world, you know, Europe and America, Japan, everywhere. And they're submitted to a joint kind of repository, and they are run under the same set of protocols, so you can compare them. This is useful to to see in the big competition about whose model is doing better. That's obviously a part of it, but it's also, well, if they're all doing a good job, that means that they're all plausible. So look at the range of change between different models that are all nice models, then that gives you some estimate of, well, the range of possibilities, because you can't rule one out. So a lot of this analysis of possibilities is done by using this set of models that are all brought together. I mean, it's not truly probabilistic because it's a bunch of models brought together. So that's what we call an ensemble of opportunity. But it's a pretty good tool given in the absence of anything else, and we don't have a fully systematic, comprehensive way to sample this uncertainty space. You know what I mean?